electron chart now. So this is going to become very useful for you, right? Because this will help you determine what charge state your atoms are going to want to be in. For the main group elements, you can just walk across and determine. So we find aluminum in group 3, right? And so it's here at the +3 state. So we know aluminum will want to take a +3 charge. How about sulfur? What is it like to be? -2. Yes. So sulfur likes a -2 charge. Right? So if we use our cross system again, I'm going to say we'll need 3 atoms of sulfur and 2 atoms of aluminum to help make this a neutral charged component. So if I say +3 times 2, that would give me +6 on the charge. -2 times 3 would give me a -6 on the charge. +6 minus 6 will equal 0. So that should give me a balanced molecular structure. So if we're going to write this one, how do we write it? Al2, S3. Very good. So we need to put the number of atoms is our subscript. That is very good, right? So this one is aluminum sulfide. And yep, the formula for that is Al2S3. So our subscripts are the number of atoms. Go down there. Very good. All right, so we did that. Okay, so when writing the chemical formulas, we've already been practicing this. The cation is always first. The anion is always last. Stable chemical formulas have to have a net neutral charge. So the positive charge has to equal the total negative charge. And we use our subscripts to show how many atoms are present. So subscripts equals the number of atoms within our ionic formula. If it's 1, you don't need to put the 1. That's implied. All right. So now we can get into naming, right? So our name of the cation is pretty easy. We just take off, or we add to the element name the term ion, to the end of it. So if we have a sodium atom that's lost an electron, we can now call it a sodium ion. That's pretty easy. The anions are a little bit harder to name, right? So depending on the element, we are going to drop the end of the element name and replace it with "ide." So for chlorine, for example, when it gains an electron, we change its name from chlorine to chloride ion, right? So it'll lose the INE, it'll gain an IDE and become chloride. Yeah, so if I say chloride, I can even drop the ion, but you still know it's an ion because it's got the IDE ending, right? Some of them are a little bit more truncated than others. Oxygen, we drop most of the end of the name of its name and call it oxide. So OXIDE for oxygen. Yes. So part of it is just getting used to seeing like the names. Nitride, sulfide, bromide, iodide, all of those would be the IDE ending. But you can be sure anytime you see an IDE ending, that means that it's an anion and has gained electrons. Okay, so for naming our ionic compounds, the term ion is dropped and the cation and anion names are placed together. Right, so the cation, again, is always first. The anion is always last. And if you have an element that has more than one ionic state, you have to use Roman numerals to indicate what state it's in. So that's going to be true for our transition elements especially. So you could see like titanium could be in a +3 state or a +4 state. So if you have a titanium oxide or something like that, you'd have to tell me what state the titanium is. It could be titanium 3 oxide or titanium 4 oxide. You'll have to tell me which ionic state it's in. It changes the molecular formula. Right, so that's very important, the charge state of your atom. So we use Roman numerals for the charge state. Yeah. All right, so magnesium and chlorine coming together to make magnesium chloride. That is its name, right? So we just dropped magnesium ion, and we just put it next to the chloride, which is the anion name for chlorine. Magnesium can only take the 2+ state, so we don't need a Roman numeral for it, right? So if it only has one charge state, no Roman numerals needed. If it has multiple charge states, which again you'll know from your chart, so you'll always have this as your resource in here, then you need to give me a Roman numeral for the charge. All right, so we have another example here. So we've got iron 3 and chlorine coming together to form iron chloride. So we did this one already as an example. And we know we need 3 chlorines involved in that bond. So if we had iron 2 coming together with chlorine, we would only need 2 chlorines to come together with that iron, right? So those 2 compounds are fundamentally different from each other. Iron chloride with the 3 chlorines needs to be distinguished from iron chloride with the 2 chlorines. And we do that with the Roman numeral, right? So we could say iron 3 chloride, that's going to tell me my iron is in the +3 state, right? Versus iron 2 chloride is going to tell me my iron is in the +2 state, right? This will allow me, if I just say the name, hey, go order me some iron chloride, you're not confused and come back and say, well, do you want iron 2 chloride or do you want iron 3 chloride? Because they're different. Which one do you want me to order, right? So you should be able to tell the formula from the name, right? And be able to work backwards and forwards from that name. So Roman numerals are always used when you have multiple ionic states that your cation can take. Yes?
So how would I know whether I want the +2 or the +3 ion?
So you would have to have some recipe or lab protocol that said you need iron 2 chloride for this experiment. Yeah, so it could be either, depending on your needs. Yep. Yeah. All right, let's see, back to... So electrons carry what charge? Yep. So if an atom is negatively charged, has it gained or lost electrons? Gained. Electrons are negatively charged, right? In its elemental state, it has equal balance between protons and electrons. The only way it can become negatively charged is to gain electrons. Because if it loses electrons, it has more protons than electrons. And it will be positive.
So when we're looking at the positive or negative statements to a random element, are we looking what the charge itself is already, or what it would have to get lose to get to 0?
So if I tell you you have O2 minus, that's the charge on that atom currently.
Okay. So
Yes, it's an anion.
Cation, okay, it's a positive.
And so how do you name anion?
It would be IDE.
You have to have the IDE ending. Yes.
Still oxide. Because cation.
Yes, it is by itself.
Or negative and negative charge.
Yeah.
And
If
negative
it's
anions
involved in a
add
bond, you drop the ion.
Wait, one time, sorry.
No, you're okay.
Since it's a negative charge, that would be anion because the cation has a positive charge. So it's O2 negative, I to the end. That's our name.
So it's the oxide ion then?
Yeah.
Okay.
Yep. And it's gained electrons.
So it has a negative charge is gained electron.
Yes.
So the anion is
Negatively charged.
Okay.
Yes. Yes, because cats are positive influences in your life. Yes. You gotta have mnemonics in there, right? Yep. All right. So this one is the oxide ion. So remember, for anions that are negatively charged, you have to change the ending to IDE. So look for that IDE ending. So in creating the correct ionic formula of aluminum sulfide shown in the diagram, so we did this one as an example, right? So it's asking how many sulfide ions are needed in the bond.
You have to turn it into separation. I love that answer. I don't know why.
And do we have all the responses? Best guesses? All right, the correct response is 3. So always try to kind of use the charge to guide you. So you can use it across, right? So if my aluminum is +3, I'm going to try a 3 for the number of atoms of my anion that I'll need. And with my anion at -2, I'm going to try 2 atoms of my cation. And then see if that will give you a balance of 0 coming out for your positive and negative charge. That will usually work. Say usually, there's always exceptions. Yeah, so make sure you know the symbol for cobalt. And then you can set up a charge box or charge diagram. Right, so cobalt has what symbol? CO. Very good. CO. Phosphide? P. That's phosphorus in the ionic form. Right, so if we want the charge, right, what's the charge of cobalt? Is there 2 or 3 there? 2. Very good. I need better glasses. And what's the charge on phosphorus? -3. All right. So if we want to find out how many atoms we need of each, right? So we can use our charges to try to help us, right? If my charge is +2, I'm going to try 2 atoms of my anion. My charge is -3 on my anion, so I'm going to try 3 atoms of my cation. Total charge, we multiply through, right? +2 times 3 will give me +6. -3 times 2 will give me -6. Add those together. Total charge on my molecule is 0. So when I write my formula, what should my formula look like?
So when we're doing that equation, we're just looking to get the negative or the 0 charge, I guess? That's
Yes.
okay.
Yes. Stable compounds have 0 charge to them. If they're charged, they're still reactive and they will continue reacting until they are no longer charged. Yeah. So they can't really exist that way in nature very long. Yeah. So Ag is what? Silver. Cl. Chlorine. In its ionic form? Chloride. Okay, so you've got your cation and your anion. Do we need to have a Roman numeral for silver? Where is silver?
And the transition.
It's in the transitions. Does it have more than one state? No, it takes a what? Positive charge of +1. Right? So we don't need to put the Roman numeral in if it can't take more than one state. So this one would be?
Do you have an extra cheat sheet? Or
Do I have a?
an extra of like the cheat sheets?
Oh, yeah. And we have all the responses. Whoop. All right, we've got silver chloride. Oh, you can't do this one yet. You're like, there's too many elements up there. Okay, let's do a 5-minute break, and then we'll come back and we'll talk about polyatomics. Kid. Here, all finished?
Yeah, I finished.
I will scratch you off my list. Thank you. So I do have kits for this week's lab for online people. I have kits for week 4 as well if you want to pick that one up.
Hey, I'm not.
It's only because I have this thing.
Oh, you have a return. Do you need 3?
No, I already got it. You want 4?
Awesome.
Thank
Tell me
you.
your name again.
Isabel Press.
Awesome.
Thank you.
Thank you.
So, I guess the first step is to get that. So, you know how like when you can switch, you can if I ever explain so going back to the formula, so it's
They're similar to the Socrative that we're doing. Yeah, there'll be multiple choice, maybe some true false, and maybe some matching in there as well. Yeah. Mm-hmm. Yeah. The homework style problems too. Yeah. Yeah.
On the test, we don't get this one, we get yours, right?
You will get that one attached to the exam, but not yours.
Okay.
Yes.
Like same thing.
You can write on yours.
Yes,
You
but
can
we're not allowed to
do.
have any of that on.
Correct. Correct. Yeah. Yeah, because if you want to write numbers on top
Right,
of
you
the
can.
families and yeah, whatever helps you.
with a charge is that it has wait, having a charge here, just like if I change the charge, so that's also
Yeah, just a reminder for the exam too on Monday. You need a calculator. You cannot use your cell phone, right? Because I will have calculators you can borrow. I'll bring them to lab with me this week too, just so you can play with them, right? Because it's good to like, exactly, practice with it. I don't want to test you on your calculator skills.
Will we need like a TI calculator or just like a little dollar store?
You need something that can do some scientific stuff. Like you need to be able to do scientific notation. Like if you're converting with Avogadro's number or something, that's a really big number. A lot of zeros like in there, right? So you want to be able to do scientific notation. The half-lives had log functions potentially. So you need to be able to use a log, off your calculator as well. Yeah. All right. So let's go ahead and jump into our polyatomic ions. So these are made up of multiple atoms that come together and they are actually forming covalent bonds, which we haven't talked about in detail yet, but they're sharing electrons. And then they also exist in this charged state. For polyatomic ions, most of them are negatively charged. There's a few of them that are positively charged, like ammonia. But you'll notice that you've got on your cheat sheet, let's go back to the dot cam, right? So I gave you a polyatomic chart. Oh, maybe. Yeah, that's up on the top of your common ionic state, right? So you'll notice it'll give you the formulas for those anions or cations if you have the cations as well. And it gives you the name of them. So you don't have to memorize these. You just have to be able to use them to bond to something else. They move as an entire unit. And if you need more than one of them, it has to be the entire unit. And so you'll need to use parentheses around it to include all the atoms that are in that polyatomic structure, right? So normally the names, like if you're going from a name back to a compound, you can tell it's a polyatomic ion because it ends in ate or ite rather than the I. Ite is usually just the binary one. There are a few exceptions. Peroxide is one of them that still has the ide ending, but there's 2 oxygens in there instead of a single one for the oxide. Right? What's another one? Hydroxide is also an ide ending one, and this one has hydro and the oxy, so it has hydrogen and oxygen in that covalent bond, and it has a negative charge of 1. All the others, I think, are ide. Cyanide is another one. Has a carbon and a nitrogen together. Okay, so again, they behave as a single unit. So we can treat them as just interacting with a cation or an anion if you have a positive one as that whole unit, right? It still has a -2 charge. So if it was going to bond with something like sodium, how many sodium ions would we need? So it has a -2 charge. Sodium will lose how many electrons? Just 1. It's in the group 1 family, right? So sodium will become a +1 cation. So how many atoms of sodium would I need to bond with sulfate? 2. Yes, because my sulfate has a -2 charge. Sodium has a +1 charge. So I would need 2 sodiums to balance that -2 charge. So the rules are still the same as we saw with our binary compounds, right? We still need to balance the charge out to 0. But this whole thing moves together. It never separates. They're sharing electrons, so it's like they're holding hands with each other. They're not going to let go, right, when they're in there. So this is just another diagrammatic way to show that chart up there. You don't need to memorize any of these again. You just need to be able to say, oh, hydroxide is OH minus. So minus just -1. Mm-hmm.
So are a lot of these acidic versus bases?
No, acids and bases are a little different. The hydroxide is basic, but that's the only one. Well, no, there are some acids in there. But we'll get to acids and bases in a little bit. I'll hold off that question on those guys. So not necessarily, but maybe. Hydrogen is like one of those things.
Are these things stable by themselves, or do they want to hold hands with one more atom so they can be stable?
No, they're not stable by themselves typically because they're charged, right? So they want to interact with something that can negate that charge, right, and make them a 0 compound. So if these are solids, they're going to need a binding partner. They're going to need a cation to be with. If they're in a liquid, we'll talk about things dissolving in liquids actually next week. Yeah, so that's a little bit different.
When you go back a slide, where did you get sodium from? Where is that?
Oh, I was just using it as an example.
Okay.
Yeah, it's not on the slide. Do you want me to write it down?
Oh, could you explain like how it?
Yeah. So this guy, right, if we're seeing sulfate here, it has a -2 charge. So it's not going to be happy by itself, right? Because it's in a charged state and things don't like to be charged. Charged things are reactive, right? So it's going to be bouncing around, bumping into things and saying, you know, who can I be attracted to that's missing electrons, right? So the sodium, if I have sodium ions, right, they're going to be in a +1 state. They're a group 1 element. They'll lose 1 electron, right? And so I would need 2 of them, right, to balance out the -2 charge on the sulfate. Yeah, so if I had sodium sulfate, right, I could write that formula Na2SO4. Yes, it just has to balance back to 0 charge.
Okay, so they just want to be positive.
They want to be 0, right? So I've got +1 here, -2 here. I have 1 of these things. And I have 2 of these ones. 2 times +1 is +2. -2 times 1 is -2. So it balances to 0 charge overall. So the same rules apply when you're making bonds with your polyatomics. But this polyatomic moves as 1 unit. You can think of it as just one thing, right? So if you have multiples, you'll have to put those parentheses around it. If there's only 1, you don't really need a parentheses because I don't have to write subscript 1 down there. Yeah. Okay. Let's do some more examples so this makes a little bit more sense. All right, so now let's combine sodium with the phosphate. Right, so we can do the same thing, set up our charge box the same way. Right, so and I'm going to be like, okay, well, I've got a -3 on my anion, so I'm going to try 3 atoms of sodium. And I have a +1 on my sodium, so I'm going to try 1 anion with that. Right, my +1 times 3 will give me a +3. My -3 times 1 will give me the -3. My overall charge on the molecule or compound will be 0, right? So if I put these together, what is my formula going to be? Yep, so I've got 3 sodiums, so I need to show that. How many phosphates? Just 1, so I can just put 1 phosphate in there. Yep. So this one is sodium phosphate. Right, and I get the name from that. I got to find my phosphate over here, right? Here. Yeah, so you got to find the PO4 3-, and then you can get the name, phosphate. You don't have to memorize those.
How do you designate when there's 2 phosphates? Is it 2 PO4?
So if I have to have 2 PO4, like say we used magnesium instead, right? So if I have magnesium, right, that is a +2. The phosphate is -3, right? So if we do that same kind of cross, I would need 2 of my phosphates, and I would need 3 of my magnesium. 3 times 2 is 6. -3 times 2 is 6. That would end up equaling 0. So my formula for magnesium phosphate would be what? PO42. To show that, I have to put the parentheses around that whole thing and show there's 2 of them. Right? So that tells me how many oxygens do I have in there? 8. Yes, 2 times 4, I have 8 oxygens. How many phosphorus atoms? 2, right? Because there's 1 in each one of those. Yes. So parentheses and the subscript goes outside it. Yep. All right. So the name for our sodium and the phosphate coming together, we just put them together, sodium phosphate. If you're using a transition metal that can have multiple ionic states, you also have to include the Roman numeral in there. So if it was iron or something like that, you would have to tell me iron 2 or iron 3 phosphate because they would be different formula. Okay. All right. So don't memorize these. You will be given the chart, and I will only use the ones that are on the chart on the exam. So those guys are fair game, but I wouldn't use any additional ones that are not on there. But you do need to know how to make the correct ionic compounds using them based on their charge. Put your box in there. Figure out how many you need of each. Yeah. All right. So we already did magnesium phosphate, right? So hopefully this looks good now to you, right? Just work across, right? And then to show that you have 2 phosphates, you have to have that parentheses around the whole polyatomic ion, and then use the subscript for how many polyatomics that you have. So in this case, you have 2 phosphates. Yeah. All right. What does this actually look like? Well, the phosphates, again, are covalently bonded. So we'll get into covalent bonding probably next week. And you can designate a covalent bond by a straight line. That means they're sharing a pair of electrons, right? So there's one electron. They're sharing them, means they spin around that oxygen, and then they spin around the phosphorus as well. So sharing electrons rather than donating them. So it's just 2 ways that atoms can bond and get to the octet state. You can do it by sharing, or you can do it by donating. So this is showing my phosphate is a little weird one. We won't go exactly into the bonding, but it has expanded orbitals. So if I have 2 lines, that means it's sharing 2 electron pairs. Right? So you can kind of draw the electrons in there in those shared states. So each of these phosphates has 3 negative charges that are held out on the oxygens. So the oxygens aren't really happy yet. They want to be at kind of -2, right? They're only sharing 1 right now. They still have space to get another electron, right? They're going to do that from the magnesium. The magnesium will donate the electron to the oxygens, but magnesium can only do 2, right? So this pairing is nice, but that oxygen's still unhappy. So it needs to go with the other magnesium, right? And that can donate 2, and then this one can donate 2 as well to those guys, so that all the oxygens end up being happy in that molecule. So in the scaffolded structure, the ionic structure of magnesium phosphate, they would be kind of oriented that way. The cations would be 1, 2, 1, 2, or maybe sharing with another phosphate, forming a lattice structure. All right, let's do a little more practice. Oh, my screen went off too. Yay. All right, so if you have your chart, what charge states can cobalt take? +2 or +3. So what needs to be in this equation or this name? Roman numerals, yes. So you should have a Roman numeral in your answer. How do you know which it takes? Yes. So cobalt has to be +2 or +3 when it's bound to one chromate, what's the charge on the chromate? How does it balance? It's -2. So what must my cobalt be? Process of elimination. Yep. Oh, let's switch the main one. There.
Oh, I think I get it. Because this one, oh, it's right here.
So first, right, I see more than 2 atoms. That means I have a polyatomic in there, right? So I need to look for my polyatomic. So I have a metal first, and then I need to see what that CrO4 is, right? So I need to come and look for CrO4, chromate. Do you find it up there?
Yeah. So I guess then for like equations like this, you find the first one like here and then the next one.
Yep. So my chromate, what charge is on my chromate? -2. Okay, so I just found my chromate is 2 minus, right? I know it's bound to 1 cobalt. So how do I get that to 0? What charge must the cobalt be? So what is my name? Cobalt 2 chromate.
Makes sense.
Yeah, so if you see more than 2 atoms, right, it's not a binary compound anymore. It's going to be a polyatomic one. And 99% of the time, it's going to be the anion that's polyatomic. So just take that first one, the metal, okay, that's your cation. The rest of it, look for it on your polyatomic chart. Yeah. All right. All right. So, first, we know manganese 4. What's the charge on my cation? +4. I've got a Roman numeral there, and it just told me, oh, that's 4. Right? So I look down, find manganese. That's Mn. It can be +2 or +4. Right? So my Roman numeral is 4 in this one. So I know my manganese has to be +4. Right? Arsenite, what does that thing look like? Yeah, so it's here. So AsO4 3 minus. So it's a -3 charge. All right. We'll try this way. 3 times 4? Yep. So my formula? Is that up there? Because there's 4 of them. Right? So my subscripts always tell how many. Right? Not the charge. How many of them? Right? So our number of atoms. or polyatomic units. All right, we have all the answers. Yeah, so if you have choices, you could test these, right? You just know, like, that bottom one, Mn3ASO42, right? You know the arsenate charge is -3. So you would know 2 times -3 is giving you a plus, or a -6, right? That's not going to balance out the -12 or +12 charge you have on the manganese. Yes?
So are these all of the polyatomic ions that we
That
know of?
exist in nature? No.
No? Okay.
No, but they're the ones you're responsible for.
Okay.
Yes, I will not ask you about any that are not on that chart.
So would you say that they're pretty common in nature, or?
Yes.
They are? Okay.
Yes. Very common in nature. Yeah.
Looking
Has
at,
has anybody heard like the sugar phosphate backbone of DNA? Yeah, you've got phosphate all over the place. Sulfates are all over the place. Yeah. Very common.
looking at acetate and benzoate, why are there 2 O's instead of O?
Yeah, so we're going to get to this because we're going to dive into more of the organic chemistry. But the way that it's written out like that suggests that both of those oxygens are covalently bonded to that carbon. Or it could also suggest that the oxygens are bonded to each other. Both are possibilities when they're written like that. In this case, they are bonded to that carbon like that. But we're totally not there yet. Yes. Oh, and you couldn't see what I was drawing. Sorry. Yeah. So, but this also could mean this. That they're bonded to the oxygen. You don't totally know until you play with the structures and see if they're happy or not. But for acetate, it's like that. Yeah. You don't have to draw that yet. Yeah, that's a couple weeks away. Yes. We have to get to the organic chemistry part first. All right. So, you can't see my lecture notes anymore. No. How about this one? All right. Maybe? Yay. All right. So for ionic compounds, ionic compounds typically will form a crystal lattice structure. So this is one of the characteristics of ionic compounds. And because of their charged nature, they're going to form a structure that allows the negative charged things to be next to the positive charged things. So if we have something like sodium chloride, right, it's going to form this crystalline lattice structure where the chlorines are next to the sodiums, right? And so you can't really distinctly tell one sodium chloride molecule, right, or compound. You can't say, oh, that sodium is with that chlorine, right? Because it could as easily well be with that chlorine or that chlorine as well. You can't really tell from the crystal lattice. So the ionic nature of it is distributed throughout that whole structure, right? When you have a crystal lattice structure like that. So this makes ionic compounds very strong, right? Because they have that ionic interaction with more than one partner, essentially, to build the lattice structure. So this lends to some of the properties of ionic compounds. They typically have really high melting temperatures and even higher boiling points. Like, so if you were in the lab and you were trying to get sodium chloride to melt, it's going to be up around maybe 600 to 800 degrees Celsius. That's really high. How many degrees Celsius to boil water? 100, right? Like 6 to 8 times higher to get sodium chloride to melt, right? So very strong interactions you have to overcome to get this thing to go into the liquid state, right? So ionic compounds typically don't melt very easily. They're very strong in their structure. All right, so high melting temperatures, high boiling points. They also tend to be pretty hard and brittle. Like, so you can break them, but you can't get them to melt easily. All right. So as solids, they can be insulating. They won't carry charges through them like a metal conductor will. They can be very insulating. But if they're in the liquid state, they can then be conductive, right? So in the liquid state, I don't know if I have all right, we won't talk about the liquid state too much yet. But as you dissolve solids, right, everybody has put salt in water before, right? What happens to the salt? It dissolves, right? It appears to disappear, right? The solid no longer is solid anymore, but it's not in a liquid state, right? It hasn't melted, right? It has dissolved, and that's different, right? It's interacting with the water molecules now, right? So we'll talk more about that after we do some covalent bonding and look at the way covalent bonds are characterized. Okay. All right. So ionic compounds can be classified as three things. They can be acids, they can be bases, or they can be salts. Right? So sodium chloride is a salt, typical salt. For it to be an acid, it has to have H as the cation. Right? So anytime you see H as a cation, that can act as an acid. So if we have H bonded with chlorine, HCl is hydrochloric acid. So you'll use that later in the lab. But H plus is considered the acidic component. When you have H plus in solution, right? So does anybody know the formula for water? H2O, right? This is a covalently bonded compound, right? So it's bonded with those water or the hydrogens and it's sharing electrons. If a hydrogen pops off, it's going to leave its electron with the oxygen. So the water molecule, if it kind of falls apart, can end up like that, right? The H plus and the OH minus. So if there is an imbalance in H plus and OH minus in your water solution, that's when your solution becomes acidic or basic. So if you have a greater amount of H plus, this is going to lead to an acidic solution. And if you have greater amount of OH minus, this will be a basic solution. Right? And if you have a lot of protons around in solution, you have a very strongly acidic solution. Acids and bases are corrosive, right? They can burn you. They will melt things, right? They're very reactive situations when you have acids and bases forming. Okay, so all other ionic compounds without these ions are salts. So most of the ionic compounds that you'll see fall into the salt category. Now we, talk about table salt an awful lot, right? Because we eat that like every day and we like that. So we always say, oh, salt, that's sodium chloride. But that's also magnesium chloride, magnesium phosphate, sodium nitrate, like all of the other things that can combine with metals. Titanium oxide, those are all salts. Right, so they get the salt classification if they do not have hydrogen or the hydroxide. So something like that, sodium hydroxide, would act as a base because it would contribute that anion to your solution. Yes?
Okay, so earlier we were talking about how gamma rays disrupt electrons and that's why they're damaging. Or do these bind to electrons and that's why, like, in specifically acids, they bind to electrons and that's why they burn us? Or what's happening?
Yeah, yes, they're very reactive, right? So that H plus wants to bind with something, right? And if it's your protein or your DNA or something like that, it's going to steal electrons away from your molecules. Yes. 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 But it's not like radiation, right? It is a physical molecule, a physical like OH, right? So those are really big. Those aren't going to penetrate like through your skin. But they will eat like your skin away and keep going. Yeah. So if you get it on you, like in the lab, you want to wash it off of you really quickly. Yes.
When you get like, I heard when you get like a base solution onto your hands, and it doesn't like burn you, but it also, I heard it like turns your skin into like a chemical soap. Is that?
Yes, kind of. Yeah. So we will actually make soap in the lab from sodium hydroxide. Yeah, and that's made from lipids. So yes, when hydroxides interact with your fats on your body, they could potentially make a soap, but they burn you. Like that hurts, right? Like it's breaking down your fats and your lipids and your proteins and your DNA and your cellular structure all at the same time. It doesn't only interact with the lipids, it interacts with everything that's around it. Yeah, so bases feel slippery, but they burn you just as badly as acids do, depending on their strength. Yeah, so acids and bases when you have out of balance of either of those in your solution. Neutral, there'll be some H plus and OH, but they will equal each other. There'll be equal amounts of H plus and OH minus in the solution. Yeah, and it's very, very, very tiny. Yeah, in a neutral solution. All right, so just some strong acids for you. So perchloric acid, HClO4, chloric acid. So you were asking, I think, about some of the polyatomics being acidic. Yes, some of them are acidic. HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroionic acid, iodic acid, nitric acid, and sulfuric acid. Very common, strong acids that you would see in a laboratory setting. All right, so you notice the main commonality, all of them have hydrogen in the cation position. Okay, so this will be an indicator for acidic compounds. Yes, generally. Water is a weirdo compound that's covalent, that also has H first, H2O. And we said that can break down into H and OH minus, but typically those two things are balanced, and that's why water is not acidic. But if it breaks down, it's got the counterbalance of the base in there as well. So the base plus the acid neutralizes to water. Okay. Strong bases will have the other half of the water molecule, the OH or the hydroxide ion. You can look for that in there. So it should be in all of them. Mostly group 1 metals with the hydroxide, and some of the group 2s make strong bases. Yeah. Right, so these are things when they mix with the water, right, they're going to fall apart, like lithium and the hydroxide. Kind of like that, when they're floating around dissolved in solution. Yeah. All right. All right, one more name. We could have done this one last time. So our MnO4, what is that one? Permanganate, charge on it? -1, right? Potassium, where is it? Group 1, what is its common charge? +1. Nice match, just as they are. Do you need to have a Roman numeral? Nope, it's in group 1. It can only be +1. Is there a Roman numeral? No, why? What's the characteristic of potassium? Potassium can only be +1. That's right. Yeah, so you don't need the Roman numeral with your main group elements. All right, we have all the answers. Very good. Potassium permanganate. Good. And do we have all the answers? Best guesses? All right, very good. So when the H is in the cation position, it can behave as an acid. And we said water was the exception because, well, water's covalent. But even if it does fall apart, it has one H plus and one OH minus, which is an acid and a base. They'll neutralize each other out. So water is not an acid or a base, but it can contribute to both of those things. Okay, let's see. So the other half of the water molecule is the anion component.
Because potassium's a positive charge.
Yeah, so acid and base nature of solutions depends on the things that make up water, right? So the H plus is the acidic component. The other part of the water is the OH minus. So compounds that have hydroxide as the anion can act as a base. Potassium doesn't really contribute to anything in that. So OH. And we have all the answers. Yes, very good. So if you're looking for acids, H is the cation. Looking for bases, OH is the anion. So what is compound A? How would you classify this one? Acid, base, or salt? Or covalent? Base. Very good. How'd you figure that out? Has a hydroxide as the anion. Okay, so there's a base. How about HCl? Acid. Why? H is the cation. Okay? Rubidium bromide. It's the salt. How'd you know that? How'd you eliminate water? Yes, this one's actually covalent. So it's not a salt. Yeah. All right. Very good. Let me jump back. Ooh. Ha. Good. All right. So we're going to, in this section, talk about the importance of ions in biological systems. So to do that, we have to think about how things dissolve. So we talked about putting sodium chloride into a solution, right? And that when you put it into water and stir it up, it like goes away, right? Like you can't see it anymore, right? It does not melt, right? It's not in the liquid state, but it's in an aqueous state. So our water molecules are covalently bonded. They're sharing electrons between the oxygen and the hydrogen to fill up both of those valence shells, right? And when they do this, they don't share equally, right? So oxygen is way over next to fluorine and has really high electronegativity, and it wants the electrons more of the time, so it hogs them, right? The hydrogen's like, that's okay, I don't need them so often, right? So when they're sharing, they spin around the oxygen like maybe 15 times and then once around the hydrogen. They're over here most of the time and then once in a while. So the charge distribution on the water molecule is slanted, right? It's not sharing equally. The electrons carry what charge? Negative charge. So there is a partial negative charge up here on the oxygen because it's sharing not fair, right? It's hogging those electrons more of the time. What does that mean for the hydrogen? They're partially positive. So when they don't fully donate the electrons, they're sharing, and every once in a while it'll spin around the hydrogen. So it's not a true ionic bond. So I'm going to give it the delta symbol. Delta positive means partially positive. Right? Or partially negative. Not totally. So it hasn't totally donated the electron over to the oxygen. All right, so this is kind of the state of a water molecule when you have your water in your glass and you're drinking it. If I add salt to it, right, my sodium chloride, when it's solid, right? I've got other sodiums that are next to each other, right? And I'm forming this crystal lattice structure with all my sodium chlorides, right? As this dissolves apart, the sodium is going to come off of the chlorine, and it's going to come over and interact with the partial negative charge of the water. It's just going to be attracted to that side of the molecule, right? And then similarly, the chlorine, being negatively charged, will be attracted to the partial positive charge on the water molecule. So in the crystal lattice solid structure, sodium chloride can act as an insulator. It won't conduct things, right? Electrons can't move through it because the charges are all bound up. But when they're floating around and dissolved in the water, they have free charges now floating around, and the water is now conductive because there are ions in it, right? You've got the sodium ion and the chloride ion. So it can conduct electricity. That is critically important for how we think. You are all doing this process right now with all these little ions inside your brain, right? Ions can carry charge. We use electrons, right, in our outlets, right? And it's powering the room. All the electricity that's being generated in our room are from electrons that are coming off of metal conductors like copper wire and things like that, right? And then you have an energy source that's sending them, maybe the solar panels generating our energy for us, right? So in the brain, we're using ions to help signal messages from neurons, right? So when you're learning, you're using ions to send signals and build brain pathways. So we're going to take a look at how this happens in our neurons, right? So neurons, also known as nerve cells, are essentially electrically excitable cells, and they're using the electric signaling, right? And what we mean by electric, right, are just ions. They're responsive to ions, both positive and negative, right, states. So we're going to essentially see how neurons work, but that's too much for our last 2 minutes for today. So just that introduction on things dissolving. Remember, the human body has how much water in it? 70%. Almost the same as our Earth, right? Yes.